Welcome to this comprehensive guide on the equations of motion. In physics, kinematics is the branch that studies how objects move without considering what causes that motion. Today, we'll explore the 5 fundamental formulas that help us understand and predict the motion of objects moving with uniform acceleration. These equations are essential tools in physics and engineering, allowing us to solve real-world problems involving moving objects, from cars accelerating on highways to rockets launching into space. By the end of this lesson, you'll have a solid understanding of each equation and when to use them. Before we dive into the equations, let's familiarize ourselves with the 5 key variables we'll be working with. First, we have displacement, represented by the letter S, measured in meters. Displacement tells us how far an object has moved from its starting position. Next is initial velocity, shown as u, which is the speed at which an object begins its motion, measured in meters per second. Then we have final velocity, represented by v, also in meters per second, which is the speed of the object at the end of its motion. Acceleration, denoted by the letter a, is measured in meters per second squared and represents how quickly the velocity is changing. Finally, time, represented by t and measured in seconds, tells us how long the motion takes. Understanding these variables is crucial because every equation of motion combines these quantities in different ways. The first equation of motion is v equals u plus a t. This equation establishes a direct relationship between velocity and time. It tells us that the final velocity of an object equals its initial velocity plus the product of acceleration and time. This is one of the most straightforward equations in kinematics. Use this equation when you know the initial velocity, acceleration, and time, and you need to find the final velocity. For example, if a car starts at 20 meters per second and accelerates at 3 meters per second squared for 5 seconds, you can easily calculate its final velocity. This equation works for both positive acceleration, where objects speed up, and negative acceleration, also called deceleration, where objects slow down. The second equation of motion is s equals ut plus 1/2 a t squared. This equation relates displacement to time and is particularly useful when you need to find how far an object has traveled. It combines the effect of initial velocity, moving the object forward, with the additional displacement caused by acceleration over time. The term ut represents the distance covered due to initial velocity, while 1/2 a t squared accounts for the extra distance gained from acceleration. This equation is essential for calculating the stopping distance of vehicles, the range of projectiles, or the distance covered by any object moving with constant acceleration. Notice that time appears as both t and t squared, which means displacement increases more rapidly as time increases when acceleration is present. The third equation of motion is v squared equals u squared plus 2as. This is a unique and powerful equation because it relates velocity to displacement without involving time at all. It's incredibly useful when time is unknown or difficult to measure. The equation tells us that the square of the final velocity equals the square of the initial velocity plus twice the acceleration multiplied by displacement. This equation is particularly valuable in problems where you know the initial and final velocities and acceleration, but time is not given. For instance, if you need to calculate how much distance a car needs to reach a certain speed, or how fast an object will be moving after falling a certain distance, this equation is your go-to tool. The fourth equation of motion is s equals 1/2 times the quantity u plus v. All multiplied by t, this equation calculates displacement using the concept of average velocity. When acceleration is constant, the average velocity is simply the arithmetic mean of initial and final velocities. By multiplying this average velocity by time, we get the total displacement. This equation is especially useful when you know both initial and final velocities and the time interval, but acceleration is unknown or not needed. It provides an elegant alternative approach to finding displacement and is often simpler to use than the second equation when you already have velocity values. Think of it as finding the area under a velocity-time graph using the average height method. The fifth equation of motion is s equals vt minus 1/2 a t squared. This is an alternative form for calculating displacement, but this time it uses the final velocity instead of the initial velocity. The term vt represents the distance if the object maintained its final velocity throughout, while 1/2 a t squared is subtracted to account for the fact that the object was actually slower earlier in its motion. This equation is particularly handy when you know the final velocity, acceleration, and time, but the initial velocity is unknown. It's less commonly used than the second equation, but it can simplify calculations in specific scenarios, especially when working backward from a final state to determine displacement. Let's review all 5 equations of motion together. Equation 1, v equals u plus a t, relates final velocity to initial velocity, acceleration, and time. Equation 2, s equals ut plus 1/2 a t squared, gives displacement using initial velocity, time, and acceleration. Equation 3, v squared equals u squared plus 2as, connects velocities and displacement without time. Equation 4, s equals 1/2 times u plus v multiplied by t, uses average velocity to find displacement. And equation 5, s equals vt minus 1/2 a t squared, calculates displacement using final velocity. Each equation serves a specific purpose, and choosing the right one depends on which variables you know and which you need to find. With practice, you'll quickly recognize which equation to use for any kinematics problem. Remember, these equations only apply when acceleration is constant throughout the motion.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.